Hi, my name is Igor, and today, together with my friend Igor, we will talk about how to make an application in our free time that helps us while working with mobile research. During the talk, we will cover the following topics: Memory 101 on mobile devices, modern approaches to solving our problems that didn't fit us, about how we created the application and what problems we solved along the way, and later how it was packed into a Docker container, trying to make USB ports on different computers together, and other issues, and of course, like, share, and contribute on a GitHub.
At first, I want to make a short step back and tell you why we decided to start developing this tool. Memory analysis was a big issue for us, and all current solutions were related to simple static memory dump with a great tool called FreeDump and further analysis on it. Sometimes we do need to check transformations in memory during runtime. So we decided to turn our ugly scripts in a very useful and platform-independent tool. It's really common situation when you are overwhelmed with work and have something to develop which simplify your life, but you couldn't find a free time in your daily routine to build that and continue repeating the same things all the time, isn't it? In conclusion, we took part in Black Hat SG and Div0 hackathon, Hacksmith 3.0, and decided that it's high time to satisfy our internal need, and of course to contribute to the community. Where this tool could be useful? Penetration testers, for sure it's rather simple when you need to check that confidential data is encrypted in memory and password is not transmitted in plain text, so you can dump and analyze. Then forensic experts. If you do pattern analysis and incident investigation, sometimes everything you need could be loaded in process memory, and sometimes it's in plain text. And last but not least, reverse engineers. It's not a secret that sometimes reverse engineers operate on heavily protected stuff. In this case, you couldn't rely on your static analysis toolkits. And for sure, runtime memory analysis approach won't help you to identify constants which were encrypted or even understand assets flow based on input transformations. Not a killer feature, but sometimes saves a lot of time during mobile app analysis. As I've already mentioned, there are already several approaches to retrieve interesting data from the analyzed application. If memory dump is possible, we can operate on static dump. It's helpful when you have non-modifying datasets and values passed into memory are not changing during program execution. First approach in our list is attaching the debugger. For sure, this method can be applied if there are no protections against debugging. It's a more stable way of analysis and less chaotic than operating on a changing memory in live mode. But if there is good detection implemented, it's likely to cost us a lot of time to bypass. And sometimes it's just an overhead to use the debugger. Next one is static analysis. Definitely there is plenty of static analysis tools which can help you with analysis if there is no protection or obfuscation, but it's still on a different level with dynamic analysis and couldn't be replaced. Certainly those approaches should go together, but in our case we assume that you haven't achieved your target using static analysis. Sometimes we all might experience many analysis complications. For example, SSL pinning, anti-debug, all types of intrusion detection. So, from memory dump, we could retrieve API calls, unencrypted secrets and constants, and if we were lucky enough, and caught it during runtime, of course. Android and iOS, two popular operating systems that power almost all mobile devices on the planet. Android and iOS have its own memory management models. While they have many similar things, with one copying another, the two can be any more different. Not necessarily because one operating system is better or worse than the other, but differences do exist in their memory management. Memory management here means how the two operating systems make the use of their random access memory. RAM can be defined as a way computers and smartphones access stored files. Unlike hard drive, RAM is temporary storage. What this means? Things that are stored inside RAM aren't permanent, like those stored inside hard drives. Since smartphones are devices with a more limited size, there is a small difference between how RAM is used on these devices versus how it's used on computers. The main disadvantage of this Android memory management is the way Google and other developers handle their apps. From the way they are built and created to how they behave in the background. Android uses Java. For good reasons, Java can run on any processor. What this means, it can be ported by many smartphone manufacturers running different hardware configuration. But the disadvantage is that it runs via a virtual machine, which is like a virtual computer layer between the actual hardware and the software. This is a huge disadvantage because a lot of memory is needed to run this virtual machine, and even more memory is needed to store both the Java bytecode and the processor machine code, as well as store the system-needed resources for translating the Java bytecode into the device's processor machine code. Lastly, this virtual machine is built around a method called garbage collection. In short, garbage collection is essentially a way for Android to recycle memory once an Android app is done using it. While this method is effective, it works by consuming much RAM. Otherwise, the system will spend too much time collecting garbage that it will ruin overall performance. Problems can also happen when users have a lot of apps running. Android's original virtual machine, Dalvik, was built in a time where the smartphone industry has yet to know what CPU architecture would dominate the mobile world. At that time, it was designed to use the x86 ARM and MIPS with room to add future architectures as needed. Since 2014, it supports x64 processors. Android devices contain three different types of memory: RAM, ZRAM, and storage. Note that both the CPU and GPU access the same RAM. So, RAM is the fastest type of memory, but it's usually limited in size. High-end devices typically have the largest amounts of RAM. ZRAM is a partition of RAM used for swap space. Everything is compressed when placed into ZRAM and then decompressed when copied out of ZRAM. This portion of memory grows or shrinks in size as pages are moved into or taken out of ZRAM. The storage contains all of the persistent data, such as the file system and the included object code for all apps, libraries, and the platform. Storage has much more capacity than the other two types of memory. On Android, storage isn't used for swap space like it's on other Linux implementations, since frequent writing can cause wear on this memory and shorten the life of the storage medium. If the amount of free memory falls below a certain threshold, the system starts killing processes. To decide which process to kill, LMK uses an out-of-memory score called OMH score to prioritize the running process. Processes with a high score are killed first. Background apps are first to be killed and system processes are the last to be killed. The following table lists the LMK scoring categories from high to low. So items in the highest scoring category in row 1 will be killed first. Android invokes on trim memory method to inform apps that memory pressure is high and apps should deallocate unneeded memory. Android can kill paused apps at any time, so apps should serialize critical state when they transition to a paused state. iPhones have less RAM than Android phones, but Apple has a reason for that. It doesn't need as much. For example, developers of an Android app can make the app to stay persistent in the background. This consumes RAM that otherwise can be used by other apps. The Android operating system that is based on Linux chooses to stop apps running in the background when available RAM runs low, in order to free up for new apps that users are opening. iOS, on the other hand, squeezes more data from apps running in the background compared to Android at a system level. Whereas in iOS devices, Apple has a more controlled strategy. In this case, the operating system chooses whether an app can do something or not when it's running in the background. What this means, iOS allows users to open more apps and having them run in the background longer after users have finished using them. Then, there is iOS that was designed to run Objective-C applications or on known hardware, which is an ARM processor. Because Apple has full control of the hardware, the company could easily make the decision to have native machine code, so it means without virtual machine, running directly on the processor. This practically saves a lot of memory requirement. What's more, iOS doesn't have the garbage collector. Instead, every object created on the operating system has a count associated with it. This is called retain count. A newly created object will be given a count of 1. During the course of the object's life cycle, the retain count can increase or decrease accordingly. But the rule here is that once the retain count reaches 0, the operating system immediately terminates the object. In fact, memory management is simply an exercise in counting. Every object has its own reference count or retain count, which is the number of other objects that are currently using the object. As long as the retain count is greater than 0, the memory manager assumes that someone cares about that object and leaves it alone. When an object's retain count goes to 0, the memory manager knows that no one needs it anymore and sends the object a dialog message. And after that, its memory is returned to the system to be reused. When Apple introduced automatic reference counting, ARC, iOS can automate the process, with the compiler inserting the appropriate retain count to the code before building the binary. This memory management capability is a major advantage over Android's garbage collection. This is, for reasons, part of why iOS devices run so fast while having lower specifications. The following figures show the state transitions involving the app delegate object. After launch, the system puts the app in the inactive or background state, depending on whether the UI is about to appear on screen. When launching the foreground, the system transitions the app to the activate state automatically. After that, the state fluctuates between active and background until the app terminates. When memory pressure is high, iOS forcibly evicts entire apps from memory. iOS finds the application will terminate callback of the about to be evicted app, allowing them to serialize app-specific state before eviction. This state is typically much smaller than the entire working set of the app. Later, when the app is resurrected, it uses the serialized state to reinitialize itself. Application will terminate only invoked on the background apps. Suspended apps and apps that are not running code but have pages in memory is terminated without notification. There are a lot of tools for memory debugging and memory leakage tracing for developers. For iOS, it's via map or tool called Leaks, and for Android, tools like DDMS or any IDEA tool like Eclipse Mat. But these tools are not really useful for our small hacking attempts. While the two operating systems have their own advantages over the other, the RAM usage and management on both operating systems are quite similar and efficient. The main difference is how they manage the RAM in the way they handle apps that run in the background. Fortunately for us, it mostly reflects in memory size we need to process or dump. And here we are happy to have Frida framework to cover ours back.
Let's move on to our history of the instrument, because it was not an instant solution, and the idea has grown and changed several times so far. Starting from last year's fragment of a work task via MVP and the hackathon, and ending with getting rid of unnecessary element along the way of simplification. In this part, we will talk about what stages we went through and how the program changed. Maybe this will give you ideas for your projects, or you can tell us how to improve the current one. The idea to build that tool came up spontaneously when one of us was faced with the task to track data in device memory again, and the classic memory snapshot didn't work as it needs. At the same time, we began to notice that in memory leaked quite a lot of interesting data that is not properly managed by the developers and contained interesting info to research. And friends from the InfoSec community advise us to take part in hackathon organized jointly by GovTech Singapore and Black Hat Asia. That's how we decided to kill two birds with one stone in 48 hours coding run. Of course, they use familiar ways to work with the memory like Frida framework and objection, but some of it did not work as we wanted. There were many flaws with projects that help dump memory, such as free dump, because the application might crash while taking a memory dump. At the same time, this is exactly what is used in objection. However, in a last version, at that time, it became possible to search for a pattern in memory, which interested us. But the main task remained unsolved. We could not track the state of memory throughout the entire application at any given time while looking for a bunch of patterns. We started with a free dump code because it has the functionality of working with raw memory, and it helped us to understand how everything works. Having got an idea of how this works, they turned to the documentation and then found a function that allows us not to take a snapshot of the memory on the file system, but to look for a necessary pattern directly on the device that gives us a performance boost. At the second stage, they have built our JavaScript file, which could already be run directly from the shell. And they found that many code examples that we encountered on the internet use only the last element of the memory array to look for a pattern in it, thus skipping almost everything else. We fixed it, but it slowed down a little. In any case, even on a big memory sizes, about 1 GB, searching for a pattern takes from a couple to 5-8 seconds, which, in our opinion, is fast. Now, it was necessary to get the opportunity to run this script in the background, and not only on one pattern, but on a dynamic list that could be modified right during the execution. As a result, this was achieved using an endless while loop on Ruby, which from time to time called a new code instance for Frida and changes to the search array while implementing thought a file socket. In general, this was our main idea, and we reached it by the end of the second day of the hackathon and got a medal. It was decided not to stop because there were many problems. There was no error handler and the correct termination of threads, poorly written spaghetti code, and much more. We began to think about how to improve UI UX and experimented with tons of frameworks and played with input, output, and control interfaces. There was even a web interface. There were also new features popping up while would be useful, and it seemed to us that it would be great. But at one point we realized that we needed not a Swiss knife, but a well-working tool. We came to the fact that we abandoned any kind of interfaces and left only the launch for the shell with several flags. It was decided to wrap everything in Docker. It was a challenge because the devices are connected via USB, but it helped us improve usability. Many algorithms have been rewritten, as well as new functions from Frida to manage memory, and the output has been replaced by structured JSON. Now, everything can be started with one comment, and we can continue to work in a familiar environment, because everything is packed into one Docker container. To more conveniently work with results that can be extensive, an HTML report is automatically generated, and raw data remains if it's integrated into any flows. And we also added static analysis on the memory dump from the device. Here and now, we talk about what was created over several iterations and more than 6 months of work. We are glad to any contributions to the advice or improved code. Also, we have several ideas that we plan to complete in a few months, and you can see them on Black Hat Arsenal at the end of September. We will tell you more about it later. Let me summarize what we have achieved, and we will move on to the equally interesting part about Docker. First, memory tracker with the ability to change the search dictionary without any interruptions during executions. we built an independent task runner layer for control JavaScript Frida, a Docker container with a built-in environment that is ready to work with most iOS and Android devices via USB port, human-friendly report and raw data for further processing, and of course macOS Catalina friendly. Now let's check a little sneak peek.
Let's move to our demo. We will run it against Instagram app installed on iPhone. They've initially pre-generated dictionary with only one word, secret, and later we will add password phrase. We can change it also dynamically, because after one iteration it will back to this dictionary and we read it again. So we can see it generates the output HTML file with lots of data and links to physical files. And it's also created JSON raw data, which can be easily parsed with different applications. Now let's move to static mode. It's run several tools one by one. Initially, it will dump info from memory device and put it in a dictionary dump test. And later, the application called Sign Search will be run against this dump, which helps us to find some patterns already used in this dump and memory, which might be leaked. And it also generates some file. We can use it later to our next steps.
It is important to note that during our work, we noticed that all the examples that used memory scan to walk around in memory in search of a pattern used only the last element of array. Therefore, it works quickly, but skips of other sections available for working with. We slightly changed the rules of walking across the memory list, which caused a slight increase in operating time, about 2 seconds. But we began to find more occurrences of a pattern which improved the result.
Now it's time to say about our environment. During many rounds of modifications on our tool, we noticed that it's always a huge mess to configure the environment for testing. This problem is applicable in the case of many other open source tools when it's not possible to test on all ecosystems. Docker really makes it easier to create, deploy, and run applications by using containers. And containers allow us to package up an application with all of the parts it needs and ship it all out as one package. By doing so, we can be assured that the application will run on any other machine. When we started testing how it's going to work inside a Docker, we stumbled upon a few issues for us. First, we was not sure if it's going to work since there were no clear solution on USB port forwarding from Mac machine to Docker container. After short lookup in this area, we found that it could be done using Docker machine, which is part of Docker setup based on VirtualBox image. Second issue was to set up all the necessary SDK packages and supportive libraries for both Android and iOS for correct interaction with them as smartphones. When it was done and devices recognized, it was a time to start having fun and rewrite our Frankenstein one more time. List of advantages was pretty huge for us. At first, it gave us a platform-independent solution, which is easy to implement in the automation pipeline. Users don't care anymore about configuring virtual environment for Python, then a VM for correct version of Ruby, and other related stuff. it became easier for us to deliver updates. Also, it was useful to keep different versions of Docker images for different tasks. Because of the nature of our tool, as a pet project, sometimes we don't have enough time to enlarge current functionality, but it takes only a few hours or even minutes to rewrite the logic on top of Frida and spawn a new Docker image based on a previous one. Now it's time to say about some disadvantages. In my opinion, it's a little of a pain to make initial setup if you're on Mac. Because you need to install a virtual box and configure Docker machine, which is not a straightforward process at the first sight. Since we did this process a few times during testing of our solution, I prepared a short guide on step-by-step setup. Currently, it's for Mac OS users only, but we'll extend it for other platforms a bit later. On Linux, it should be way easier to set up, and Windows users should expect the same amount of pain. However, it was never tested on Windows machines, actually. And yes, you can find this guide on my GitHub account page, which is on this slide. Let's move on and see the demo part. We'll start with Android device, and in our Docker container you need to plug in your Android. So in our case it's Nexus 6P, and as you can see, LS USB output shows that it found. And after you entered ADB devices command, you should approve ADB debugging on your device itself. Then make sure that Frida server is up and waiting for incoming connection. Then you can launch our MIMIOP tool with a bundle ID as a parameter and -d mean dynamic mode. And now we are seeking for our secret value, which is entered in a password field. And as part of application logic, it probably purged from memory. So if you make a static dump, it's a big chance that this value won't appear after static dump. But since our tool is working in a multi-threading mode, it's trying to capture the interesting values during different states of execution. So we'll see how it's gonna look after we give some time to finish our tool working. As we can see, there is no new data in memory, so we can safely shut down our process. And now let's check it inside the Docker container itself without any beautification. And as you can see, in a deleted region of Delvik main space, there is our confidential value, and it means we are good in this case. And in a real world scenario, as we can see, the nearby string, it's like string entered. So we can try to look for this value next time and suppose to have a password next to it. Now let's check the same routine with iOS. So make sure your iPhone connected. Then we check if USB Max process is up. So it means our Docker container is marked as trusted computer for our iPhone. Then we just grab the value of our testing application, and in iOS case we are using the app name as a parameter and -d for to enable dynamic mode. And here we are seeking for one really secret value that's supposed to be recovered from this sample app, and part of the phone that we'll manually enter later, and username value just to check what we could grab from the memory. Maybe there is some hard-coded values. Then you can continue using your application or just give it a time to finish execution and memory analysis. As we can see, there is no new data in memory. And it's safe to shut down the process. The same thing, we can open the log manually. So we can see our entered phone value and the secret value that's supposed to be recovered using any other method. And since our pattern for phone matching was a pretty dump, I would say, there is a lot of wrong results and false positives. So this part is to be optimized in the future. And as you can see, there is also some static assets recovered from the memory. Fortunately, we can filter it using this path value. We can define if it's from real volatile memory or it's a just static asset loaded into it. So, as I already mentioned, our tool is to be updated in the future, and we'll try to provide many other options of using it. Our next updates will be focused on beautifying the output and make runtime dump chunk size more flexible. Of course, we are open to hearing from you which options could be useful in your working scenarios. Because today we are modifying workflow manually for each of our tasks and executing it from separate Docker container. So, as I already said, any suggestions and ideas about collaboration are very welcome.
That's all for today. New updates will be shown at Black Hat Asia Arsenal 2020 in September, if nothing is cancelled. This tool is a very young project, with a huge backlog, with improvements that are rolling in production very slowly, since it's developing only on weekends. We hope that going public that this project will help us to hear your needs and make tool a better version of itself, with help of open source community. We are going to add some features later, like Docker Linux support and more real-life use cases. We will also be happy to hear any feedback on where you found tool to be used. Thank you. Now, if you have questions, do not hesitate to ask it. On the screen, you also see two links with Docker image and standalone tool.